Hello everybody, here are your video notes on solving systems by graphing. So you already had video notes on solving systems by elimination and substitution. That was review, and then you had some bookwork problems to review that as well. Before we move on to systems in 3 variables with x, y, and z, I want to talk a little bit more about the third way of solving a system that you've already seen before. So again, you have seen elimination and substitution. That was in the video. And so elimination, substitution. This video is going to be graphing to solve a system. There are 2 more methods that you'll learn later on in the year. They involve matrices, so we're not there yet. So just in general, as a reminder, a system of linear equations is a collection of equations in the same variable. So you should be filling this out on the note sheet I gave you. It should be taped in your notes. If I have a solution of a system, there's always going to be a solution that is an ordered pair. So you'll solve for x, you'll solve for y. Just realize that that's actually an ordered pair, x, y. You can always write it as an ordered pair. And it's an ordered pair that satisfies both of your equations. And a system sometimes is going to be in slope-intercept form. So this is an example of a system here. A system also can be, if I'm just making a system up right now, in standard form. 5x minus 3y equals 8. Both of these are systems. It really can be in whatever form that you want. Just realize that when you get a solution, so for example, the solution to this one is 2, 3. To solve or to check the solution of a system, all you have to do is plug it back in. And when you do plug your x and y back into your original system here, you end up with true statements. So 3 does equal 2 times 2 minus 1, and 3 does equal negative 2 plus 5. Another way of thinking of a solution is it is the point of intersection. And this is the one that sometimes people forget. Whenever you have a system, you can always graph it, and it always ends up being the point of intersection. Now, whenever you solve a system, there are 3 possibilities for solutions. You can get an ordered pair, and that would be exactly one solution. You can get infinitely many solutions, or you could end up with no solution. Now, if you were to picture a solution with exactly one solution, then that would look like 2 lines that intersect. And 2 lines that intersect, that could only happen if the slopes were different. So right here it says describe the slopes of the lines whose equations form a system with exactly one solution. That would be saying the lines have different slopes. If the lines have different slopes, their rate of change is different. And what that would look like here, so if I classify the system, you're going to learn 3 new vocab words here. If the slopes are not equal, like we said right here, they have different slopes, then the system has exactly one solution. And what that would look like, if I do my best here drawing, really is just any 2 lines that have different slopes. And one could be positive, one could be negative. They could both be positive or negative, as long as they only intersect at exactly one point. And wherever they intersect, that is the solution to the system. So we have exactly one point of intersection here. And that point of intersection, x, y, is the solution. So I have intersecting lines. So the intersection is key here. We have 2 lines that intersect. Now, if I picture a system where whenever you solve it and you do elimination or substitution, you could also end up with a system that has infinitely many solutions. Now, if you have 2 different lines and there's infinitely many solutions, the only way that could happen is if you have the same exact line. So if I had one line that looked like this, and then another line that was the exact same thing. That's the only way there'd be infinitely many points of intersection. And what would happen there when it says describe the slope for infinitely many solutions? What that would mean is the lines have the same slope have the same slope because they're the same exact line. If you have infinitely many solutions, not only do they have the same slope, they also have the same y-intercept. Just keep that in mind. Even though it only says describe the slope here, just realize you need the same y-intercept. They have to be the same exact line here. So unlike having intersecting lines, like what was in the first case, we are going to have the same lines. So same lines, and they are going to be parallel. And here there are infinitely many solutions because of the same exact line. So if the slopes are equal and the y-intercepts are the same, they're also equal, then the solution has infinitely many solutions. And there's not just one point of intersection, every point on the line is a point of intersection. The last case is you could have no solution. So picture when you do your substitution or elimination, you end up with a false statement, meaning there's no solution. The only way you could have a system of two lines with no solution is if they just never cross. Because again, where they cross, that point of intersection is the solution. So if they never cross, they're never going to have that solution that you're looking for. The only way that could happen is if we have parallel lines. So for no solution, the lines have the same slope. So that's how I'm going to describe the slope for this type. In addition to be parallel, it should be a different y-intercept. If the y-intercept was the same and the slope was the same, you'd be looking at this situation. You want different y-intercepts but the same slope. You have parallel lines. There is no solution here. And there's no points of intersection. That is a third and final case that you can have. So right here, if the slopes are equal, the y-intercepts are different, the system has no solution. Now there are three vocab words that go with these three types. So our three types of systems are exactly one solution, which is intersecting lines. We also have infinitely many solutions. That's the same line. And we have no solution. That would be parallel lines. So the three vocab words I want you to write underneath here. And for our vocab words, if I have a system with exactly one solution, I can classify the system. That's why it's called classifying here. I'm going to classify it as what's called consistent. Consistent means there's at least one solution. There is at least one solution here. There's actually exactly one solution. So in addition to calling it consistent, I can go one step further. I can classify it even more and call it independent. An independent system has exactly one solution. So it's consistent because there's at least one, and then it's independent because there's exactly one. Now right here, when I have the same line and I have infinitely many solutions, I can still call it consistent because there is at least one solution. But because there's infinitely many solutions, I'm going to call this dependent. And dependent means infinitely many solutions. So for the third case where there's no solution and I have parallel lines, I can't call it consistent because there's not at least one solution. I'm going to call it inconsistent. Inconsistent just means no solution. You can't classify it any further than that. So it's either consistent and independent, consistent and dependent, or inconsistent. Those are the three types. Now to finish up your video notes here, what I'm going to have you do is go to the second little slip of paper that I gave you. And on this slip of paper, I want you to tape it down, and then I want you to graph each and then classify it using the three vocab words we just talked about. After you do that, I want you to state the solution as an ordered pair, or if there's not an ordered pair, state infinitely many solutions or no solution. When you graph it, notice you might be looking at this thinking, how am I going to graph it? It's not solved for y. Well, you know how to solve literal equations for a single variable. So solve each of these for y. That should be relatively simple by now. Graph them together, so both of these go on here. Both of these go in here, and these go in here. And like it says, graph it, classify it with vocab, and then state the solution. We will check tomorrow in class what you got here, so make sure you do this all the way out. And I will see you in class. Bye-bye.